Okay, welcome back. We're looking at the mech assessment that you guys have just done for summer 2020. So let's have a look at what we've been asked to do on this question. We're told that at a time t is equal to 0, so some start time, parachutist falls vertically from rest from a helicopter which is hovering at a height of 550 meters above the ground. Parachutist is modelled as a particle and falls for 3 seconds before her parachute opens. While she is falling and before her parachute opens, she is modelled as falling freely under gravity, 10 meters per second squared. So just to quickly get an idea of what that looks like in my head, here's the ground, like so. Here's my person. I've been told that that distance there is 550 meters. They fall for 3 seconds, so I've been told that while they're falling, that's 3 seconds there, that the acceleration during this point is, due to gravity, is 10 meters per second squared. My question then goes on to say, can I use this model to find the speed of the parachutist at the instant her parachute opens? As I've been told that this works with constant acceleration, then the acceleration due to gravity is modelled as this, as being 10 meters per second. So I know it's a constant acceleration type problem. So I now know, because it's constant acceleration, I can use SUVAT on there, SUVAT. I know my time here was for 3 seconds. I know my acceleration was 10 meters per second squared. I don't know my final velocity, but that is what I'm being asked to find. I certainly know the speed I started at. That was 0 meters per second. And my distance, I don't know. It is definitely not 550 meters, because that's how high it was above the ground. And as you can see from my drawing, that's not my distance that I'm using. So when I'm looking for an equation that has all of these points in it, without distance, the only one that will do that is v is equal to u plus at. Substituting what I've got there, final velocity is what I want, so this is nice and easy, plus the acceleration was 10, and the time that was going to fall for was for 3 seconds, giving you 30 meters per second, and that becomes your final answer. Part 2 of this question. When a parachute is open, the parachutist continues to fall vertically. Immediately after her parachute opens, she decelerates at 12 meters per second for 2 seconds before reaching a constant speed, and she reaches the ground with this speed. The total time taken by the parachutist to fall 550 meters from the helicopter to the ground is t seconds. Sketch a graph for this one. So we're looking at a velocity time graph. So nothing else. Get 2 axes that deal with that. Right, now we start trying to pull together everything that happens here. So at time t equals 0, you've been told that you're falling freely under gravity, and because of that you have a constant acceleration, and so I just draw a line up like this, and we worked out from our previous question that that goes up to a speed of 30 meters per second. Put that in for that axis, and this is measured in seconds. Parachute opens, and we have constant deceleration for 2 seconds. We'll do this on my graph, and then I'm told that after my constant deceleration I will reach a constant speed and I'll hit the ground at that speed. So that's what my graph is looking like. I can get some timings in here. After 3 seconds, we're told that it remains open. Now the other useful bit I can put into my graph is this speed here. If I am decelerating at 12 meters per second for 2 seconds, well, this must mean that I've lost 24, or my speed has decreased by 24 meters per second. If I started at 30 meters per second, by the time I've taken away 24 meters per second from that, I'm now down to a speed of 6 meters per second. So that looks like my completed velocity time graph. Question 1c actually asks us to go ahead and find this value of t. So I could look at doing this for SUVAT, but if I did this for SUVAT, the things you'd have to bear in mind were that you'd have to do SUVAT on this part first, where your acceleration was accelerating at 10 meters per second squared. You would then have to do SUVAT on this bit afterwards, where your acceleration was going down at 12 meters per second squared. And then finally, you'd have to do SUVAT on this section of the graph, where your acceleration was constant. So every time you were trying to do or use SUVAT, you'd have to make sure that your value of acceleration remained the same for that section which you used in SUVAT on. Taking a similar idea, we can also recall that the area under a velocity time graph was the displacement covered. What this means is that I can now work out the area of this part of my work, then work out the area of this part, and finally do something about this last rectangle here. So my math starts looking like this. Area of a triangle, so that's the base, which is 3, multiplied by a height of 30 all over 2. That makes 45 meters. For this trapezium shape, half the sum of the parallel sides, so one of these parallel sides is 30, the other of these parallel sides is 6. So that's showing 30 for that height, that's showing 6 for that height. And now you multiply it by the distance between those two parallel sides, which is the time difference of 2 seconds, going from 3 to 5. So a quick calculation on this. We're going to half something, we're going to times it by 2, so they cancel themselves out. So I'm just left with 30 plus 6, giving me 36. Right, so let's go back to what we've got so far. In this section we've done 45 meters, in this section we've done 36 meters. The whole part of this section here represents 550 meters, which means I'm now going to work out how much area is represented by this bit, and in so doing I can do nice bit of calculations just to work out the value of t. We can say our 45 meters was for our first section, our second section was 36 meters, our third section, that's this bit here. Let's have a quick look for the area for that. We know we've got a height of 6 in there, so this is just length times width. So our length, if you like, was 6, our width goes from here to here, so that gives me a distance of t minus 5. Or I can just write that as 6 brackets t minus 5. So those three distances added together give me a total of 550 meters. Quick bit of rearranging now gives me the following. I was asked to round this to the nearest whole answer. Final answer. In part D, we've been told, in a refinement of the model of the motion of the parachutist, the effect of air resistance is included before her parachute opens. And this refined model is now used to find a new value of T. How would this new value of T compare with the value found using the initial model in part C? Well, if we've added air resistance into it, we'll expect it to slow things down, so the value of T should increase. And that's all we're looking for this bit. We don't need to give any reasons why, well, because they've not asked for that point, so that's good enough. In part E, it says, suggest one further refinement to the model apart from air resistance to make the model more realistic. So first of all, you can't put air resistance in as a refinement. Whenever you're asked to go back and suss out what's wrong with your model that you've used, you've actually got to go back and reread the question. Try and find where the assumptions have been made. So let's have a look. At time t equals 0, a parachutist falls vertically from rest from a helicopter which is hovering at a height of 550 meters above horizontal ground. The parachutist, who is modeled as a particle, and that's one of the things, falls for 3 seconds before her parachute opens. While she is falling and before her parachute opens, she is modelled as falling freely under gravity, which is fair enough. The acceleration due to gravity is modelled as being 10 meters per second. You kind of know that that's got to be an improvement because we've got a better value of gravity as 9.8 meters per second. When a parachute is open, the parachutist continues to fall vertically. Well, if you've looked at people parachuting, and you might not necessarily be aware of this one, but you don't tend to just fall vertically once your parachute's opened. You tend to be dropped from a plane, so you've got some forward motion to start off with. So there's a bit of horizontal motion mixed up in the vertical motion. Immediately after her parachute opens, she decelerates at 12 meters per second. Now this kind of implies that your speed or your deceleration suddenly changes. So at 1 minute you're going at 10 meters per second, and now your parachute's open and suddenly you're going at decelerating at 12 meters per second. That bit should happen rather smoothly, but we've assumed it happens instantaneously. What else we got? For 2 seconds before reaching a constant speed, and she reaches the ground with this speed. The total time taken by the parachutist to fall the 550 meters from the helicopter to the ground is t seconds. In a refinement of the motion of the parachutist, the effective air resistance is included before her parachute opens. And this refined model is now used to find the value of t. So nothing in this last section. So if I just have a look at what I've got here then, almost for free I'm given the following points. So I've been told the parachutist is modelled as a particle. So we haven't taken into account her dimensions. I'm going to put that one down. By far the most obvious one was gravity. Use a more accurate value of g. We could have said the parachutist doesn't continue to fall vertically. So we could have said that the parachutist doesn't fall vertically. So the parachutist doesn't fall vertically. And this section here, immediately after a parachute opens, she decelerates at 12 meters per second. So we can state that we don't have a constant deceleration. Things that you can't state, we do have a constant acceleration that's down to gravity. So given an answer of we don't have a constant acceleration would be wrong. The mass of the parachutist or the weight of the parachutist doesn't come into account either. So you can't state. So the mass or weight won't affect the speed that you are falling at. And if you want proof on that, just Google masses falling at the same time. You should find some nice videos on that. Anyway, that concludes that question.